Welcome everyone to Bodhi Unified Flow. This is where we simplify complexity and amplify performance. I'm absolutely thrilled to be your guide today. We often think of lean as this super modern invention, right? Maybe something born in the late 20th century. But today, we're kicking off an explainer we call the Lean Revolution. In this first part, we're going to dig into the actual pre-industrial and early scientific foundations of it all. We'll be looking at the early visionaries, these massive, mind-boggling factories, and the fundamental theories that literally, permanently altered how human beings build and produce things.
All right, let's take a quick look at our roadmap for today. We'll start with the pre-industrial archetype, examine the scientific turn, compare the philosophies of Taylor and the Gilbreths, check out Ford's continuous flow, and then wrap it all up with a summary and our references. Before we step into the time machine, let's set our focus on exactly what you'll take away from this session. By the end of this explainer, you're going to be able to trace the true pre-industrial origins of mass production. You'll also be fully equipped to analyze the core principles of scientific management, clearly distinguish between time studies and motion optimization, and really understand both the operational impact and the severe human cost of continuous flow. Honestly, grasping these deep origins is absolutely crucial. It's the secret sauce to mastering modern operational efficiency. Okay, let's jump right into Section 1, the pre-industrial archetype. We are looking at operational synthesis in the Venetian Arsenal.
So our story begins way before the modern factory. We're talking about a highly secure, state-regulated industrial marvel built all the way back in the year 1104. The Venetian Arsenal was just a staggering achievement of engineering and logistics. To put it into perspective, look at this number, 45. This facility spanned 45 hectares. Imagine over 80 American football fields dedicated entirely to building warships. It literally dominated roughly 15% of Venice's total landmass. Surrounded by 2-mile-long ramparts and 15-meter-high defensive walls, it was the largest industrial complex in Europe before the Industrial Revolution, operating as a total powerhouse for 8 straight centuries. And the vibe inside those walls? The sheer intensity of the labor was legendary. It was a place of such frantic, ceaseless activity, with boiling pitch and thousands of workers moving in this crazy synchrony that it actually inspired Dante Alighieri. He drew a vivid comparison to it when creating his vision of the underworld in his famous work, Inferno. It was chaotic, for sure, but also a highly orchestrated environment, a true harbinger of the industrial times that were still hundreds of years away.
Here's what's so fascinating. Centuries before Henry Ford ever thought of an automated line, the Venetians had already pioneered the core tenets of mass production. They relied on centralized state shipbuilding, perpetual physical flow, and a rigorously structured division of labor. But the real kicker, they implemented standardized, replaceable parts. Think about why this is such a game changer. If a Venetian warship got damaged in battle, they didn't need to hunt down a master carpenter to carve a bespoke, custom replacement piece. No way! They could pull into a friendly port, grab a standardized rudder off the shelf, and be back at sea in hours instead of weeks. It's basically modular assembly, centuries ahead of its time. Moving right along to Section 2, the scientific turn. This is where we transition from craftsmanship to analytical measurement.
Notice this vast chronological gap in our timeline. We had standardized parts and perpetual flow up and running in Venice in 1104. So why did it take nearly 800 years, all the way until 1911, to actually formalize scientific work and motion analysis? Well, the answer comes down to mindset. For centuries, human labor was viewed as an art, a craft you pass down through generations. It took a massive, fundamental shift in thinking to view work not as an intuitive craft, but as a mathematical process that you could measure, analyze, and engineer. During that long evolution, 19th century thinkers like Charles Babbage stepped up and completely changed how we define work itself. Babbage shifted the focus from just looking at how long a person worked to how far the material actually moved. He helped shift the measurement of work from a pretty subjective equation of force multiplied by time to a strict physics calculation, force multiplied by distance. Essentially, he was saying, look, the time you spend sweating over a workbench is totally irrelevant if the material doesn't actually progress. Measurable output and the physical distance a product moved toward completion became everything. Which brings us to a really fun part of the story. Section 3, Taylor versus Gilbreth. Compressing time versus optimizing motion. So, Frederick W. Taylor walks into these early factories and basically sees total inefficiency. Workers were just using what he called rule-of-thumb methods, basically doing things however they personally felt was best that day.
For a factory trying to scale up, this was disastrous because it led to wildly unpredictable output. So in 1911, Taylor intervenes radically. He formalizes shop management. He argued that management absolutely has to develop a precise empirical science for every single element of work. Plus, he mandated that managers must scientifically select, train, and match workers to specific tasks to hit peak efficiency. He wanted to permanently remove the guesswork from the factory floor.
And that sparked one of the greatest philosophical debates in industrial history. In one corner, you've got Frederick Taylor and his trusty stopwatch. His absolute obsession was compressing the duration of operations. He wanted sheer speed and maximum output above all else. But in the opposing corner, we have the brilliant engineering duo Frank and Lillian Gilbreths. They argued that just slapping a stopwatch on a task and telling someone to go faster was fundamentally flawed, and frankly a bit cruel. Instead, they pioneered motion studies. They believed that if you fix the human ergonomics and just eliminate the unnecessary physical movements, well, the speed naturally follows. Their approach actively reduced worker fatigue and prevented injuries. It was the ultimate clash: time compression versus motion optimization. All right, on to Section 4, Forward and Continuous Flow, Scaling Efficiency at the Rouge River Complex.
Now imagine taking all these scientific principles, standardized parts, precise measurement, optimized motion, and scaling them up to a level that still drops jaws today. That's Henry Ford. The Rouge River Complex was an absolute behemoth. We're talking 1.6 kilometers by 2.4 kilometers. It housed 93 individual buildings and an astounding 16 million square feet of factory space. It's the ultimate manifestation of continuous flow. Literally, raw, unprocessed rubber and steel went in one door and fully drivable cars rolled out the other.
You have to hear the profound mathematical impact of this system. Ford forced the work onto a moving mechanical conveyor belt, pacing it at exactly 6 feet per minute. He took that generalized craft work and stripped it down into 84 highly distinct, incredibly rigid steps. By doing this, he didn't just improve the manufacturing cycle time, he completely obliterated it. The time to assemble a single automobile dropped from over 12 grueling hours down to just 1 hour and 33 minutes. I mean, that is an unprecedented explosion of productivity.
However, to truly understand this operational history, we have to impartially examine the flip side. This structural efficiency carried extreme human costs. That high division of labor effectively transformed workers into specialized cogs within a massive, unfeeling machine. Think about it. The severe repetition of executing just one of those 84 rigid steps thousands of times a day under strict timing constraints, it induced heavy cognitive and physical fatigue. It totally stripped away all craftsman creativity, and it generated immense systemic labor friction that rippled across the entire industrial landscape. And that intense human toll really brings us to a profound realization. It reminds me of what Albert Einstein once said, that fundamental ideas, not complicated formulae, are the beginning of every physical theory. The crucial takeaway for us here is that lean methodology and continuous flow, they aren't just about stopwatches, mathematical equations, or automated conveyor belts. At their core, they are deeply rooted in the fundamental philosophies of how we view human beings, how we value effort, and how we define waste in our daily work. Finally, Section 5, Summary and References. Let's quickly synthesize what we've covered today.
Let's take a quick moment to solidify our journey. We've definitely hit our learning objectives today by mapping a truly fascinating evolution. We saw the Venetian Arsenal prove that high-volume flow and modular assembly are actually ancient concepts. We learned how Frederick Taylor banished guesswork by bringing empirical measurement right to the shop floor. We saw the Gilbreths prove that true, sustainable efficiency has to respect human ergonomics. And finally, we witnessed Henry Ford's scale continuous flow to completely change the world while simultaneously exposing the breaking points of extreme labor division. Now, for those of you looking to really master this subject, and I highly encourage it, these foundational texts and research papers form the academic backbone of our session today. From Frederick Taylor's original principles to modern analyses of waste, these are absolute essential reading for any serious practitioner of operational efficiency. Before we wrap up, I'm going to leave you with this one final provocative thought to chew on. We've seen how the principles of flow and motion optimization completely transformed the highly controlled indoor environment of the factory assembly line. But as we prepare for part 2 of this series, ask yourself,
How must these rigid, predictable principles adapt to actually thrive in the chaotic, weather-dependent, and totally unpredictable environment of a modern construction job site? That is exactly the challenge we're going to tackle next time. So keep optimizing, keep questioning, and I will see you next time right here on Bodhi Unified Flow.